Swayam Prabha. Digital India. Educated India.
So, today we are going to look at some cases of failures in embankments of slurry ponds. And as I have told you, in India most of the raisings are done by the upstream method. So, let us look at why these failures take place and how can we take remedial action. That means you have either seen a sign of distress or actually some failure has taken place. How quickly can we make the pond operational again? So, today's topic is remedial measures for slope failures in embankments, dikes of slurry ponds. So, normally such failures are not reported in downstream method of construction, but there are very few cases of downstream method of construction in the country. So, most of the failures that we are going to do are by the upstream method. So, just to recall that this is an ash pond and where the ash has breached and has come out. This is another tailings impoundment in which there has been a failure of the slope. Here there has not been any failures, but you can see vertical erosion and seepage paths. You can see a wet. Can you see the wet downstream face? Quite clearly the phreatic line is not being captured. If the phreatic line was captured, you will have a dry slope. And this also shows small movements in not small, large movements on the downstream face of an upstream raised embankment. So, what are the causes of failure? What we have normally seen are two causes: absence of an internal drain and clogging of an internal drain. Now, why should an internal drain be absent? So, if you look back at the tailings ponds or ash ponds which were constructed 10, 15, 20 years ago, at that time one had not anticipated such immense pressure that you will not get land for disposal of tailings and ash, and you had thought that these ash ponds would be 5 to 10 meters high, right? And at that time, for a 5 to 10 meter high embankment, it looked like a road embankment. And typically you are not putting chimney drains or horizontal drains in a road embankment. So, what was done was you would take local soil, make an embankment and start pumping the slurry behind in that pond. And after the first 5 years, if the pond became full, you would take either the ash or the tailings and put another upstream embankment and cover it with soil so that there was not much of dust which would flow. So, if you look at the very old ponds, there is a very high probability that the original dike did not have an internal drain. And normally construction records may or may not exist. Also remember that constructing a chimney drain is not a simple task. It is a thin vertical element, right? And if you do not do it properly, you may make the drain, but it may get clogged with time. Either the width is not sufficient, or if the width is sufficient, then the gradation has not been mapped using the filter criteria between the ash, between the embankment material and the drain. You all know the filter criteria? You remember filter criteria? There are two issues. When you make a chimney drain or a blanket drain, so between the soil and the drain, or let me say between the fine material and the coarse material, we have to have a criteria. What is the criteria? The coarse material should have a higher permeability than the fine material, so that it catches the water and doesn't allow it to go forward. Suppose I make a drain with the same permeability as soil, what will happen? Water will come into the drain. Since it cannot take it out at a faster rate, it will go across the drain. So water will not go across a drain only if the permeability of this is much, much higher than the permeability of the soil, because water is coming from this side. So when we say it's a drain, we say the water falls like this and goes like this. For that, the permeability has to be higher. Agreed? However, the other issue is, while the permeability may be higher, the material should not be so coarse that the fine particles of the soil can go into the drain. So there is a restriction of how coarse the material of the drain can be. So there are two criteria. One is higher permeability. Second is fines should not migrate. Of the coarse material. And the second is fines should not migrate into coarse material. Now you will do this if you have not done it already in your slope stability course, but quite clearly if I make a grain size distribution on a log scale, let us say this is the fine soil and this is the coarse soil. So for the permeability to be higher, the criteria requires that D15, if I take this 15%, let us say this is 100%. So this is D15 of the finer material and this is D15 of the coarser material. So the requirement is D15 of the coarser material to D15 of the finer material should be greater than 5 or greater than equal to 5. You remember permeability of sands? There is some empirical formula. Permeability of sands, Hazen's formula. What is the formula?
C times D10 to the power
D10 square. So what it says is that permeability is governed by the fines. D10 is the size below which 10% of the particles lie. So permeability is dependent on the square of D10. In that sense, it could also be the square of D15. So if the D15 of the coarser material is greater than D15 of the finer by 5, it's likely that your permeability will be in the ratio of square, 25 times. So your permeability is that much more higher. This is what this does. But the other criteria is, if you make it very coarse, then the fine materials will start to pass through, right? So suppose I have a clay soil and in front of that I have gravel. Now fine, the gravel has a permeability more than 100 times or 1000 times of clay. But the problem is the fine particles of clay will migrate through it. So we try and now make it smaller so that the fine particles cannot migrate. So what is that criteria? That criteria is that D15 of coarser to D85 of the finer should be less than equal to 5. So if I take D85 of the finer and this is D85 of the finer, What is this trying to say? That D15 of the coarser to D85 of the finer should be less than 5. If by chance the coarser material was here, then what would happen? D15 of the coarser material would be very large in compared to the D85 of the finer material. Sorry, this should be here. And that would mean that the fine particles could pass through the voids. So this criteria prevents the migration of the fines. This criteria prevents the migration of the fines. So you have a chimney drain, you have a blanket drain, you have a rock toe, and the idea is that when the water is high, it should be caught by this. And similarly, when you are raising, then the phreatic line passes through this. Now let me take a peripheral embankment and a slurry pond. This may be low phreatic line, this may be high phreatic line. It is missing. The vertical chimney drain and the horizontal blanket drain is missing. Let me do some stability analysis. This is a real life problem. Here is the dike made of the local soil. Some properties are given to you. You can't probably read this, but this value is 3.27. So when you make a starter dike of a local soil without seepage, you may have a factor of safety of 3.27, sorry. Now, when the phreatic line is low, this is the phreatic line, and please see it does not meet the downstream face. Phreatic line is high means that this dotted line will meet the downstream face. So the factor of safety falls to 1.82 from 3.27. Still no failure, it's more than 1.5. However, now let me make the phreatic line higher. My phreatic line is high and it meets the downstream slope. That means now I'm going to get a wet face. When I get a wet face, I know that flow is occurring parallel to the outer slope on the downstream face. Factor of safety is down to 1.1. This is less than 1.5. This is not acceptable in a long-term case. So this embankment does not have acceptable factor of safety. So the absence of an internal drain will always cause a problem when the phreatic line is high. Now let's go forward. So during the high phreatic line, I have a low stability of the slope. How are you going to remediate? I know it. It's 1.1. It has not failed so far because it is above 1. But tomorrow if an earthquake comes with it, it will fail. So now you are the designer and you have captured the problem. The Professor Datta told you phreatic line must always be controlled and not towards the downstream flow. So how are you going to solve this? How are you going to remediate this? If I have a starter dike and I don't have a chimney drain and my phreatic line is coming like this, how can I remediate this? Well, if I have a phreatic line and if I want to remediate this, I need to do some stabilization. Okay, I need to do some stabilization. So if I have a phreatic line which is coming out here, now I know that I have a problem. What kind of remedial measures would you take? How do you stabilize this embankment? Well, one thought is let me go and make a chimney drain inside. Now the pond is working, there is water behind it. How do you make a chimney drain? How do you make a blanket drain? Can I make this? Not possible. Maybe I can make a vertical trench and make this, but this is just definitely not possible. Maybe I can drill some horizontal holes to make the drainage. So it's difficult. So normally what we do philosophically is, if I have space on the downstream side, not too much. See, the requirement is the phreatic line should not reach the downstream surface. I can make a berm here. If I have 5 to 10 meter space, which normally is available, there may be a road or something, then I put a berm. Have I caught the phreatic line? Please answer my question. If I put a berm here, have I caught the phreatic line? No. If you put the berm here, the phreatic line is going to go and become this. Before you put the berm, you must put an interceptor drain. what was not there earlier. How do you make the interceptor drain? In the same place you have the downstream face. Before you put the berm, you put a sand drain. Now you put the berm. Okay? I am using the word sand drain. What I mean is a more permeable drain. Now what happens? Now you are able to intercept the phreatic line. That means you have your phreatic line will come here and go out from here. Now your downstream slope is this one now. Your downstream slope is this one. Now this slope has no wetness, no water flowing parallel to the outer slope. So this is now a remediated slope. A stabilizing berm with an internal drain is the solution for an embankment which was originally poorly designed. The only requirement is that you need some space on the downstream side, typically 3 to 5 meters, to keep your phreatic line away. So this is a stabilizing berm. So let us see what we do in the case that we were studying, where the factor of safety had fallen to 1.1. In this case, the factor of safety had fallen to 1.1, and a stabilizing berm is made, and an internal drain is provided. Therefore, the phreatic line does not reach the downstream face. Let me do the stability analysis. Same problem as before, the phreatic line is high. Okay? Please see, it's coming and meeting this. But you have got a stabilizing berm, therefore the phreatic line is going down here and coming like this. Factor of safety increases from 1.11 to 1.62. You are not going to have a wet downstream face, you are not going to have low factor of safety. This diagram is actually a mirror image of the what does a stabilizing berm look like? A stabilizing berm will be nothing but some additional soil or ash or tailings along with a drain and along with a rock toe and a toe drain. So typically a rock toe will look like this. This is your ash or tailings or soil. This is sand, this is gravel, this is cobbles and boulders. Let me go back. I am looking at this. Now you can always make the stabilizing berm of cobbles and boulders, but cobbles and boulders are not easily available. They are very expensive. So you have to make use of the local soil or the material in the pond, which you can do for the stabilizing berm. So the stabilizing berm is made of the same material, and this is the rock toe. Any questions? Yeah. Will the factor of safety depend on the width of the berm? The question being asked is, if instead of 3 meters, I had made it 5 meters, the stabilizing berm, please see the critical failure surface here. The stabilizing berm is more towards the resisting side. This side is the resisting side. So the wider the berm, the better the factor of safety, because it stabilizes, it acts against the driving forces which are bringing the soil down. So the wider the berm, the better it is. So you have to optimize it. What is the width of the berm which gives you a minimum factor of safety of 1.5? Because this will mean more earthwork and require more land area on the downstream side. But definitely a wider berm is a more stable. I mean, I can also do a mid-height berm here. That will even give me, see, because once you increase this width, all that will do is increase the resistance on the downstream side. So this is another form of a berm. Here of course, the entire rock fill or boulders or cobbles have been used instead of the local soil, but this is more expensive. However, the width has been reduced. So, I am just showing you that this is a berm which is being constructed with the ash itself, and I want to show you the rock toe which is critical. This is the toe drain, this is the cobbles and boulders, can you see that? This is the gravel, that is the sand, coarse sand, that is the fine sand, and that is the ash. So many layers of transition filter. Why? Water should come through this, but no fines should come. So, ash is silty sand, sandy silt. Ash will not go into fine sand will not go into coarse sand will not go into gravel will not go into cobbles and boulders, and only clear water will come through. So, this has to be designed and constructed with great precision. So, if you are able to make this berm, then you can also do the upstream raising. We just show you the same thing. We had made this berm and it had gone to 1.6. Now, we do the upstream raising also. The water is coming from here, being caught by the chimney drain, coming through here, coming through here. Still the factor of safety is more than 1.55. So, you can do the upstream raising after remedial action on the original dike. So, I will take up two case studies very quickly. In one case, the embankment was breached, slurry had flown out, but the thermal power station was operating. So, you can't keep this, okay, I will take 6 months to make the embankment. The field engineers want the embankment to be rectified the next day. So, this was the original dike design which was given to us: soil, sand drain, toe. If this sand drain is not made properly, it is a very thin sand drain. It can malfunction very easily. Sometimes you are not able to establish, the design does show a sand drain, but you are not able to establish whether the sand drain is actually operating or is it clogged, unless you go and see this downstream side of the face. So, this one had failed, and this is the profile of the failed soil, like that. And this is probable failure surface, this is the probable failure surface. So, what do? This is the ash pond. There are two ash ponds, so temporarily they have closed this ash pond because it has failed. There has been some overtopping. Now, you have to repair it. If you want to take up a brand new problem of stabilizing it by completely excavating the failed portion. You see, what is one option? One option is excavate the whole area, recompact, because the other pond is working, right? But before you can excavate, you have to dry out the ash. The ash is full of slurry water. See, the crest has only fallen from here to here. So, here the issue is, what do? In this case, we put a stabilizing berm. This was able to give us the solution. This is the critical slip surface now. But there was a problem. The crest had to come down. They also wanted us to rebuild the crest. And the thing is, this is now all loose material. I am not excavating this material. I am putting the stabilizing berm in front of the material, because excavating it and recompacting it will take months. So, we have to work with what it was. So, the other options that we looked at was to create this crest here. This is your stabilizing berm, okay. So, there were two options which were examined, one here and one like that, and these are the slopes 3.3:1, 2.8:1, and we had to put a drain on this. Please remember, we have to intercept the phreatic line and it should not reach the downstream face, and there were vertical chimney drains and the drains put on this. So, finally, the section which was adopted was this downstream slope 3:1 with some berm. So, there was a chimney drain, and then the balance drain was on the original loose soil, and these were thick drains because maybe the original loose soil will settle a little. So, you took that settlement into account and gave thick drains. If you look at the details, it looks like this. That is the failed material. First put a blanket drain, then make this, then put compacted soil, then put another drain. So drain it as often as possible. So 1 chimney drain, 1 and 2 horizontal drains, and 3 a bottom horizontal drain, and that's the new crest. So on the original failed material, the stabilization was done. Now if you do the stability analysis, the water would come here, the phreatic line would come like this. For this loose soil, take the phi dash for loose material and see what is the factor of safety. And this was the solution for stabilizing this embankment. Luckily, we had this entire distance available to us. The second case which I am going to discuss with you is a tailings dam in which complete failure had not taken place, but the embankment was beginning to move. You could see sloughing. Sloughing means material wanting to move forward, but no slurry had come out. So the embankment was just stable, but you could see the seepage on the downstream side showing that the internal drain was not working. So this is the original slope here, very steep. Okay, and you can see this is 190, this is 206, so this is 16 meters high. This was the starter dike probably, and there were some upstream dikes as well, but made in a very casual manner. So we said that, look, we would like to put a drain on this. First we wanted to stabilize the lower portion, then we wanted to put a drain, then we wanted to put the stabilizing berm, and then cover it up the end. Sorry. In fact, when they had started noting some wetness on the side, right? Then they had put a rock waste. Typically what a field engineer will do when he sees anything becoming wet or sloughing, he will say, all right, please put coarse material on it, because fine material can come through coarse. But what he did not do, see, this dam was made of tailings material. There was another tailings pond nearby, they had used that. So 8 is loose tailings. What has he done? 10 is rock waste. So to stabilize this, he has put rock waste in front. He has not put a filter between the two. So now he has put the rock waste. Behind that is the tailings. The tailings are gradually coming out through the large voids of the rock waste. So the whole thing is a mess. You go to the site and he'll say, sir, I put so many tons of waste, rock, and still it is not stabilizing. The milky water is coming out. We have to now re-engineer the whole problem. And see what was done. You wanted to put a drain on it, so that if any seepage takes place, it is intercepted. So on this you can put a sand drain. On the tailings material you can put a sand drain. On this rock toe, can you put a sand drain? No. The rock, you put sand, it goes into the voids, right? And you say, all right, no, this is free draining, so I'll not put any sand. Okay, you put a sand drain here, but the tailings will still come out from here, because there's an interface between the tailings and the rock. How do you prevent this tailings material from coming out by putting a drain at the top? It doesn't work. So you have to re-engineer this thing so that you can put a sand, you can prevent the tailings from coming out, and then you can put the stabilizing berm. So here are some of the interesting things. Where there was an inclined drain, we just put the sand on top of the tailings, because tailings are silty sand and you can put sand on it, no problems. Where there was rock waste, can you put sand on it? No. On the rock waste, first you put gravel. Gravel will not go into the rock waste, it's bigger. On top of the gravel, you put coarse sand and gravel. And on top of that, you put sand. So 3-layer system was used. And remember, importantly is, this entire stabilizing berm was made with tailings. It was made with tailings. So therefore, if I go back, I had the rock waste, then the gravel, then the coarse sand plus gravel, then the sand, and then the tailings on top. So that is the way in which we constructed that interceptor drain on the downstream face. And then we had the rock toe, the sand drain, and this is the rock toe, cobbles and boulders, and here you have from the sand to the coarse sand to the gravel to the cobbles and boulders. On the top of the tailings, you have to put a soil cover. No problems. The tailings are silty sand, sandy silt, local soil could be put, right? But it was a dry climate area. So the operator could not assure us that he will be able to irrigate this top soil cover and have grass on it. If there is no grass on the soil will erode with time and the tailings will become exposed. So we said no. He said, I have a lot of rock waste lying around. So we said, all right, if you can't assure us irrigation and green grass all the time, then I go from tailings to rock waste again. So my front fascia would now become grey instead of green because of rock waste. However, on the tailings we will go to sand gravel, coarse gravel, cobbles and rock. So we have to put 3 layers before I can put the rock waste. If I put the rock waste directly on the tailings, the rainwater will come, it will go into the rock waste, it will come out and bring out the tailings. So this is extremely, extremely important. So in the end, I would like to say filter criteria, filter criteria, filter criteria. Whether there is flow or no flow, fines should not be able to migrate into the coarse voids of the next material. Here was a case where there was a rock, on top of that we had to put a sand drain, and to do that we had to put so many layers of filter criteria. So if you design your filters well, if you design your stabilizing berm well, you are able to intercept the incoming phreatic line. For example, in this solution, now what will happen? When the reservoir is full, the phreatic line will be developed, but it will be caught by this drain and it will come like this. And this is the stabilizing berm. All this will remain dry, even though it's made of tailings and a cover and a drain, and this will stabilize the whole embankment, which otherwise is sloughing and is very close to failure. So with this, we come to the end of this lecture, where all that I have introduced to you is the concept of remediation of failed embankments without having to dig up the embankment. The ideal solution is empty the reservoir, bring down the slurry levels, dig up the embankment, make the embankment again, this time with a proper chimney drain and a blanket drain. That you have to compare with the cost of remediation with a stabilizing berm and the fact whether you have got place on the downstream side or not. If you can't close, say you say no, I have only 15 days, then I have to bring back my slurry into this pond, then the only way to do it is to build up the stabilizing berm with a drain behind it and build it to the top, because the earthwork is lesser than redoing the entire embankment. Okay? So this is a good concept about how to remediate failed slopes and have a stabilizing berm, but if you don't put a drain behind it, then the stabilizing berm is not going to work, because the phreatic line will again reach the downstream face of the dam. Any clarifications or any thoughts come to your mind? Yeah.
Sir, in the filter criteria, we have D15 and D85.
This is the Terzaghis filter criteria, which was given several decades ago. They are better filter criteria now.
How
But
do you carry out the grain size distribution analysis of cobbles and boulders?
question asked is, how do you carry out the grain size distribution of cobbles and boulders? Well, you have large size sieves. It's still a sieve analysis. So if you are dealing with what are your maximum sieve size for sand? 2 mm or 4.75 mm. That's the difference between gravel and sand. So from 4.7 mm to 300 mm, you can get sieves of any size. If you don't get them, please manufacture them. Take strips of steel and make, suppose you want to make a sieve of 100 mm, how will you make it? You need the mesh size of 100 mm. Na? So take strips, weld them together so that the mesh is 100 mm by 100 mm. So what is above it? So you can make sieves of various sizes, but in the market also they are available, definitely up to 100 mm plus they are available. So you have to do the grain size distribution, but the quantity of soil that you need or the rock fill that you need is very large. How much soil do you need for doing a grain size distribution of sand, silt and clay? 200 grams. But if you want to do grain size distribution of cobble size material, one cobble may weigh a kg or more. So you should be using 1,000 kg of soil, or if not 1,000, at least 100 to 200 kg of soil. So the representative sample must be large enough for getting a grain size distribution of soil. Yeah.
Other than this stability criteria, is there any maximum permissible settlement for upstream wells?
Question asked is there any maximum permissible settlement for upstream method? So the embankments that we are constructing by the upstream method are all flexible embankments, and they work on the principle that if any embankment settles, the crest will be raised. These, see, the slurry deposited material will settle with time. Luckily for us, it is not like clay that it settles over 2 years or 4 years. These are all silty sands and sandy silts, so the settlement takes place over a period of a few weeks or a few months. So when you are making your raisings, by the time you finish constructing your embankment and rolling them, the settlements have already occurred. So your final crest widths are pretty stable. If there are incremental settlements which occur later, then you are already expected to raise the height of the crest. So these are flexible elements. There are no limits on the settlement due to cracking or due to any other factors in this. Intuitively one feels that in slurry deposited waste there will be a lot of settlements. If it is time dependent settlement, suppose you have very high fines, then you are in trouble. Why? Because after you have made the embankment, if you get 10, 20, 30 centimeters of settlement, then there is gradually sinking. But both in ash ponds and in mine tailings ponds, drainage is pretty quick and you don't get time dependent settlements which are that significant. Most of the settlements take place while the embankment are being constructed.
So when we are putting the stabilizing berm on the downstream side, though we are lowering the phreatic line, but we are also increasing the weight on the slide, the weight of the soil over the slip soil. So is not it causing a
Question being asked is, stabilizing berm is put on the downstream side, not on the upstream side. So the stabilizing berm is put here, the next raising will be here. So what is bothering you?
Sir, if I consider the slip circle,
Yeah.
which was considered earlier without that stabilizing berm,
Yeah, earlier slip surface may be like that.
now weight of the soil,
Yeah, but now if you look at it, it's like this. So please understand, this is the weight of the soil which is pushing it downwards, and this is the weight of the soil which is resisting. So the weight of this soil is adding to the resistance. Are you appreciating this? This was the original failure surface. This was the downward force. Now I have put this stabilizing berm. If I extend the original surface, then this force is acting this way because the slope is on this side. So the stabilizing berm is acting against the driving forces of the earlier mass of the embankment. So this stabilizes, this increases the factor of safety. The new, after the stabilizing berm is put, the new failure surface will be here. This will give you lower factor of safety this, but still this, since there is no phreatic line here, it will give you a factor of safety which is above 1.5. Okay. So this is the original failure surface, critical. This failure surface, the factor of safety will rise hugely. This is the new critical failure surface which will still be within acceptable limits. Okay. All right, we'll stop here. Have a good day. All the best.